Welcome back to Maison African Motifs. In this case, we are going to consider as an introduction, which is the basics or the part of our module 7, working with the center of fluid pressure. So it is actually very, very important that we deal with the introduction and also manage to work out the questions that you're going to have later on so that you can be able to understand everything that has been ex explained in this introduction. We are talking about the center of what? Fluid pressure. So, in actual sense, what we are going to be working with is the depth. It is the depth that we are dealing with for the fluid pressure. Remember, pressure is part of our engineering, guys, as we are dealing with engineering. As we consider fluids, they have pressure. So in our concept, we shall be actually dealing with liquids. So we want to know the depth that that liquid can have, the water, whatever that you're given, that it can have from the water surface, from the given water surface. We want to know what is the depth from what? From the water surface. So that depth of the center of pressure, it is to be calculated, and there are so many things that you need to consider as it is an application of our area moments. So this one, it is an application of our area moments. So we must have the distance, the depth, which is taken from those moments, area moments, which is the second and the first area moment. So, guys, I'm not going to dwell into the theory of the fluid, the pressure. We know this from our science. We've been doing working with that and other subjects that we have, which is especially for those who are doing mechano techniques. Yes, we've got something there about these fluids. So we're not going to dwell much into that. Our major case here is on the calculations to be made. The calculations that are to be made. And these calculations on the center of the fluid pressure, you will be calculating the depth of the center of fluid pressure. That is the major aspect that you're going to have there. So you're going to understand me very soon. Calculating the depth of the center of fluid. All right, of the fluid what pressure. We can determine this one, which is a basic formula that most of you guys you are used to because you've got that one in your formula sheet. All right, which is fine. The depth of the fluid pressure can be calculated from the second moment of area. Second moment of area. All right, everything over the first moment of area. The first moment of area. So also, I have explained some of the exams without this introduction. So remember, our second moment of area is taken from the integral of r dA. All right, remember your distance r and dA for the strip area that you're going to consider. So that's A to B. So basically, I'm going to explain. Do not worry about this. So this is squared for the second. When it is area moment, it's just going to be r dA like that. But for second, you square the r there. So that's from A to B. So I explained with question papers, guys, when you're dealing with question papers, in most cases, we just want you guys to understand a certain concept so that you can just use it to answer question papers and so on. So since we now have the introduction, this is what you can use throughout. All right. So where we are given the limits for the y, remember whenever I was dealing with the limits for the y, I was using C and what? C and D, which is okay. You can use that. But I'm going to maintain A to B so that will be together even if you are using your formula sheet, you know that, okay, this is A and B simply representing what? The C and D that you used to. So in order for you to understand me in this case, I want us to go back to our areas before we consider this section. When we are calculating area, because there's a section that will complicate things if we do not understand this. When we are calculating area, that is any area, we must consider the strip that is used. Is it horizontal? Is it a vertical strip? All right, remember, area between, when you're given something like this, then you've got the vertical strip representing for x. It means this is y in terms of what? Y in terms of x from our limits a to b. So our area can be calculated from the strip of x, which is y dx, taken from a to b. Remember that concept. Area with respect to x must be affected with the strip that is for x. Okay? Which is something else when you're dealing with the area moments, they oppose that, remember? So when we have got this a vertical strip, we consider that its area with respect to x. It is the same thing when you are given a horizontal strip. So I'm going to focus much for the horizontal strip because it is the one that we are going to use in our calculations for this class that we are going to have as we are dealing with what? The depth of the center of pressure. As long we are dealing with that, it is the horizontal strip that we are going to use. So I'm going to explain those steps later on. So the strip that we use always, it is a what? A horizontal strip. So that is why I'm going to focus on that one much on this case here. So let's say you're calculating an area. Let's just a basic one. From what you are used to, a basic one. You have got your function. We have got the graph that is being drawn, whatever that you have. Let us say something, all right? Let us just say something like this. Then these are your limits, all right? That we're using from C to what? From C to D, which I said in our case, we're just going to maintain as A and B, but this is what you were used to, okay? Then you were saying, this is my strip, which is our horizontal strip. And this function, in order for us to determine its area, as these limits are for y and the strip as it is indicating, it must be x in terms of y, remember. X in terms of y. So that if we are to calculate the area from the strip area, it is going to give us x, which is a function of what? Which is a function of y. So that is x times dy. X, a function of y. This one. So this is the strip area. Integrating, if you are now integrating, you are now obtaining what? You are now obtaining the area, which is now the integral of given those limits C to D and the X. You are now substituting that X as it is, whatever part that you are given here. You are now putting those limits, C to D, and our X being what? Being a function of Y. Remember that. So here, it is a single piece that you are calculating an area here. It is a single piece, this one. So you won't realize that there is a 1 which was actually being used here on X. We're supposed to write it 1 times X, but we're not seeing that 1 times X. We're not seeing this concept because it is just a single portion that you are dealing with. But let's consider a condition whereby the area that I'm calculating, it is for 2 sections, and these 2 sections, they are equal. Maybe you can just consider the issue of a circle. Remember the concept of a circle. Or maybe they're actually, it is or an ellipse. But as long the 2 regions, they are going to give us the same thing in terms of our area. All right? Let us say we've got something like this. Symmetrical about the y-axis. All right? In this case, since I need the strip form, remember I need the strip for y, so let me put it this way. So I need something that is that can be symmetrical. Something that can just be symmetrical about the x-axis, something like this. Okay? Where you have got your strip, which is okay. And those limits that you are using, let's say we are talking about this point from C to D, and this is our X in terms of what? In terms of Y. You have got a condition where the area on this side, this section, this area, is equal to the area that is here. It is exactly the same in terms of the area. You have got the exact area there, which is the same. You can do this. You can calculate the area of a single part. Remember, when you are talking about the area, guys, x-axis can be a limit. So you can work from 0 to a certain point. So you can see that of these 2 sections that we have, the area of what is above is the same as the area that is below. So in that case, I can use one section. I can use that a single part or a single section to calculate area. I can use it to calculate area. Then I just multiply that area by 2. Take note. I can use a single part. I can use this one on top, the one that is on top. I use it to calculate area this way. Then I find that area, I simply multiply by 2 because the area that is above is the same as the area below. So in a condition that you are multiplying the area times 2 because they are identical pieces that you are given there. Identical, same. They are identical pieces that you're given. 2 of them. So it is area of 1, you multiply it by 2. So meaning to say, when we had that the area of the strip concept, if we want to consider them at once, it is going to be given as 2x dy instead of us writing as x because there are 2 of them which are the same. So now you want to find your area, you integrate just like what we had before. But we can just include that 2 here on our dA on the strip part to show that we have got what? 2 identical portions involved. 2 identical portions or pieces or parts that are being involved. But we had to consider at once, all of them at once. So that is why you have to multiply by 2. Someone could have worked a single part, then multiply it by 2. You can do that. You work a single part, you multiply it by 2. There are graphs like that. You consider a semicircle, a circle, maybe that a piece of a circle. If you're dealing with the 4 parts of a circle, then you multiply by 4 because you've got 4 identical parts. 4 identical parts. This is what you used to have when you're dealing with what? With area. Remember that from the strip, the area from strip, which can give us the area later on by integrating and using our limits. 2 identical portions. So this is the one that we are going to consider here when we are dealing with the depth of what? Center of fluid pressure, because we are going to say we put a tank. Let's say we are considering a tank, all right? A tank that is, or a container that is holding water. So the container that is holding water, it is going to be symmetrical about the y-axis. Symmetrical about the y-axis, meaning to say it is subdivided into 2 equal parts by the y-axis. So we have got 2 ways. When you choose the water tank to be below the x-axis, when you choose the x-axis to be your water surface, so we can have the tank below. So if it is a rectangle, if it is any shape that you are going to have, it will be symmetrical about the y-axis, meaning to say we'll be having equal distance from the origin to this point. This is equal distance that you're going to consider there. Symmetrical about the y-axis, meaning to say the area on this side here, this area here, this one, it is the same as the area of this one. So on your calculations, you are going to include the 2 to show that they are 2 identical portions. This is where it plays a role now. All right. So this is what you're going to have. So like I said, there are 2 conditions where you are going to have the tank or whatever that you are given there below the x-axis, as you take your x-axis to be the water surface or the water level, or you can have something which is above. So I have done most of the question papers with our tank below the x-axis. So I'm just going to maintain that one so that we do not have what? We do not have confusion. So this is it. Whenever we are to do this, I'm going to write the steps, do not worry. Whenever we are to represent that tank that is containing the water, we have got 2 sections that are identical, and always it is the horizontal strip that is used. That is why there I was just focusing on the horizontal. It is only the horizontal strip that is used. Only horizontal strip is used. So that's, we are considering the limits for y, horizontal strip. All right, gonna consider the strip for y. If it is like this is the strip for x, remember. So the strip for y, it means we are considering the limits for what? The limits for y. Remember our concept, guys. The strip for y, it means the limits are for y. Where in our case, these limits for y, they are affecting the tank or the retaining wall. I'm going to explain later on between the 2, because you can consider a water canal, which is the dam. Then we have got something that is immersed into that water canal, taking the shape of the water canal or taking the shape of the dam, which we can call it a sluice gate, or a door installed in a canal to control the water. So there are two things that we are considering there. So we can just say a tank. Let's here I'm just giving a basic thing like a tank. That is the sluice gate, the one that takes shape of the water canal. So that is our retaining wall tank. So these limits for Y here, they are for that retaining wall. The limits for Y are for the retaining wall tank. Retaining wall tank. Not the canal. It can happen, yes, that the retaining wall tank that you have there, it is fitted, it is fitted to the canal. Okay, let me explain this too before I start my calculations. A canal is simply, we've got something like this because we are going to use that part of a water canal. A water canal. Or we can just take an example of a dam. All right, just but we are it's an opening channel carrying water, this one. All right, opening channel an opening channel carrying water. All right, so it carries water. An opening channel carrying water. So what does it do? It carries water. Take note, it is like you have got a dam. Then inside of a dam, you have got a retaining wall inside, or you've got something that you put again inside. That is, a water canal is the mothership. This one, it is the mothership, the one that you contains the retaining wall is inside, is found inside of the water canal. So they can give you the properties of the water canal. All right, they can do that. They can give you the properties of the water canal. The properties of the water canal that you are given, the water canal is the one that is directly fixed to the water surface, as of our example that we are dealing with this one below the x-axis. So this will be our water canal. It is directly fixed to the water surface. It is that part that is carrying the water. It is just like our dam. So you're saying this is our dam. This is the water surface. So when I'm saying there is a retaining wall, or maybe there's a tank, whatever that you put, it is something that we are going to put inside, taking the shape of the water canal because it's on the wall. It is taking the shape. So it can be, let's say, we put a retaining wall. Then the retaining wall, it is in the shape, direct shape of a canal, and it is filled with water to the top of that canal as it was like this. Guys, when it is like that, our retaining wall and our water canal, they are just identical, one and the same thing. So the properties of the water canal are the same properties of what? Of the retaining wall when it is like that. Please understand me here. The retaining wall can be like this. It can be taken to a certain point. I want you to see this, guys, the difference. This is our retaining wall. I want to just save it at once, or let me use a highlighter. This is our, all right, it's too big. I want you to see this, guy, so that you understand those questions that gives you a canal and the retaining wall. This is our retaining wall, this one. Are you seeing it? It is taking the shape of the water canal. But the difference of this one, it is that it is taken to a certain length or certain height below the water surface. Let's just say 1 meter below the water surface, like this, or 2 meters below the water surface. All right. So we have got our canal, which is what? Which is in red, which is our dam. Then we have got the retaining wall, this one, this piece, this one, this piece. It is taking the shape of the canal, which is very true. But our retaining wall, our retaining wall is taken maybe 1 meter or 2 meters below the water surface. Let us just say 1 meter below the water surface. Here I said the limits for y there are for the retaining wall tank, not the water canal. No, not the water canal. The retaining wall is like a shaped gate or a wall fitted into the canal. It is fitted into, it takes the shape of the canal. So when it is maybe 1 meter below the water surface or 2 meters, it does not affect that let's say it is 1 meter. It does not mean the canal is going to move. Guys, the canal is our channel that is carrying water like a dam. Okay? So a dam is not affected by what you are going to put into inside, to say like let's say we put a tank or maybe something inside of a dam. It will just go to the depth of that dam, to the depth of the dam. The dam is not going to be affected where we see now our dam is now like this. The canal is now changing its position from where it was. If here the height of the canal, let's say this was the height of the canal, this one, let's say the height of the canal is 4 meters. It will remain like that as 4 meters. It is not affected. 4 meters. They mention that the retaining wall is 1 meter below the water surface. They are telling you where it is starting to say below the water surface, it is 1 meter below that. That is where we are going to insert it. This is where we are going to insert our retaining wall, 1 meter below the water surface. So the height that was originally there of the canal is not affected. If it was 4 meters going down, it means at this point, guys, we will be at -4. That one is not going to change. So this one is -1. Remember, 1 meter down. So this one is -1. This one is -3. So the limits, these ones, -1 and -4, the limits. Remember, I said it's 4 meters. The water canal is 4 meters going down. The canal. It is what? 4 meters. It does not, this does not change. It does not change this one. To say 1 meter down, then we are going to see now at -5. No, it's not going to be like that. It is our storage tank. This is our storage opening like a dam. So its depth is not affected by what we are going to insert inside. It remains with its depth. But take note, you are not using the height of the water, like the limits of the canal, to calculate whatever that you're going to calculate, which is the depth there. You are not going to use those limits. You use the limits of the retaining wall. So our retaining wall, in our case, our limits are for y. So y is greater than or equal to -4, less than or equal to what? -1, which we said we are going to take them as A and what? As A and B. Yes, C and B, the way that I was explaining from the question papers, but this is now we have got an introduction. Let's use something that can be universal also with our formula sheet. A and what? A and B. A and what? A and B. Of the retaining wall. We are talking about what is of the retaining wall, not the canal. Not the canal. The canal, it is our limiting point. It is our limiting point, the canal. It is our limiting point to say whatever, guys, that you are going to immerse, it cannot exceed the height of the canal. It cannot exceed that. So they say it is 1 meter below, it is 3 meters. You find the retaining wall down here. You find it down here. Maybe it is what? Maybe it is 3 meters. You find it down there, maintaining the depth that it was. If this was -5, guys, it will remain at -5. Whether they said this one, it is 3 meters below the water surface, you having your -3 to what? To -5, where 5 is the height of the canal. But you are limited now on the retaining tank from -5 to what? To -3. This is the part that you'll be using for your calculations. You don't use the whole canal for your calculations unless they say that, let's say we've got a canal, and this canal is in the shape of maybe triangle, whatever that you're given. Then when they give us a condition or even a semicircle, guys, any shape, it can be any shape. This is our canal, all right? But in this canal, the retaining wall, now this one, it has got the same properties as our canal, like the dimensions, everything. It is not given that it is 1 meter below the water surface. No, this statement is not there. It means, guys, our water canal and the retaining wall, they are on the same points. They're like this. So here we cannot say we are calculating using the water canal values. No, it is the same thing. Remember, the retaining wall, it takes the shape of what? Of your water canal. So when you are not given that, to say it is 1 meter below, your canal is the same. It is actually identical to the what? To the retaining wall when it is like that. When you are not given to say it is 1 meter below the water surface or 2 meters, whatever that you're given, your canal will be exactly equal to the retaining wall. But here, when you are given that it is the retaining wall is 1 meter below, it is affected from -1 to -4. -4, which is what? The height of the canal. Just like that. So this is what we have. So like I said, all right, let us just, we said the water canal is an opening. What about the retaining wall? The retaining wall, so guys, use this to answer, to understand your basics. So is like, so this one, it is just like a shaped, all right, let me put this way in a simpler term, is just like a shaped gate. A shaped gate or a wall, all right, or wall fitted, or wall fitted into that canal, into the canal, into the canal, the one that we were talking about, into the dam or the canal, the one that you fit into is your retaining wall, or they can say it's a sluice gate. It's a shaped gate, so they can say it's a sluice gate. It's whatever that is our retaining wall. So for calculations, only the retaining wall or the gate is used, not the whole canal, only the part of what. So thus take the shape, all right, so since it is fitted, thus takes the shape of what? Takes the shape, takes the shape of what? Of the canal. So it takes the shape of the canal. Okay, so remember I said the canal is this is our an opening that is carrying water. So always a canal is fixed. The canal is always fixed to the water surface. It is always fixed to the water surface or the water level, the water surface on top. It is fixed to the water surface, the surface of the dam, whatever that you're given. So its width is the water surface. So the width of the canal is the what? Is the water surface. So its its width is the what? Is the water surface. Is the water surface. Its width, the width of the canal represents what? The water surface. Then okay, so we talked about okay, for calculations, and not this one. You must note this one now. This one you must note it. Note that. You must note that. Only calculate, or for calculations, it is only the Solusgate, which is the plate or the retaining wall that you use for calculations. Do not consider the canal. You consider the what? The retaining wall. So are made, calculations are made on the retaining wall. On the retaining wall. Not the water canal. No, no, no. Not the water canal. You don't calculate for the water canal. The water canal is our dam, guys. So you cannot calculate for the whole dam. You calculate only the part that is carrying the water. Remember, it is the depth of center of the fluid pressure. So the depth of what? You need the depth of the liquid that is inside, the water that is inside. So you do not calculate the whole thing, the whole canal or the whole dam, the part that is carrying water, the retaining wall. Where am I now, guys? Notice now I'm talking about water. Now I'm ending up writing water instead of a wall. The retaining what? The retaining wall. Calculations are made on that. So I'm going to talk about later on the calculation, this and that. All right. So this is it. A water canal. Then the gate, that one with the retaining wall, we already talked about this, guys. So I'm not gonna put much into that. The retaining wall, or they can call it the Solus gate. It's just a specific gate that is installed in a canal, as I have mentioned before. A specific gate installed. Remember, we said it's installed in a canal. It's inside a canal, so it takes the shape of that canal or the shape of the dam. All right. So it is used to control water flow. To control water flow. Okay. So you only work out that part, not all the gate. So for calculations, our retaining wall, same as what the Solus gate. You only do calculations on the Solus gate, not the whole canal shape. So remember, the Solus gate, it takes the shape of the canal, but it's not a canal. It is a part that is made having the shape of the canal, but it's not a canal. So, meaning to say, the Solus gate or our retaining wall can be adjusted. Let's say it is just a condition where you are not given the canal. They just give, maybe it's a continuous flow, but we need something that will carry the water. Then we place our Solus gate. The Solus gate can be adjusted to say, when we say 1 meter below the water level, it means the Solus gate is affected, guys, 1 meter below the water level. So if it was having, let's say our Solus gate was having 4 meters, when it is 1 meter below the water surface, we are going to have that 4 meters of the gate. Then we are saying from the 1 meter below, this is -1. So -1 minus 4, we're going to end up at what? At -5. It is adjustable. We can move it in, up and down. We are not affected to say the canal is like this. It is just about the Solus gate. They are not mentioning about the canal. You just take direct. But when they mention about the canal, now you are limited, dear guys. The gate, yes, it is there, but it is in within a limit of the height of the canal, whether it is 1 meter below, because of the canal. The canal is limited, so the gate can be 1 meter below, but it will be limited to the height of the canal up to -4. It cannot exceed that because the canal is not adjustable. It does not have those movements of up and down. So once they mention this water canal, pay much attention. If they do not mention it, it's a free will that is happening to the what? To the sluice gate. It follows the consideration to say, okay, 1 meter, and it has got its own height that it had before, which is the 4 meters, which is the height of the canal. It is affected. So, okay, once you place it, yes, it must maintain its height, but the position now where it is going to end up, it is going to end up at -5. So here they are simply telling you that -5 is the height of the canal from the water surface at 0 to -5. It is the height of the water canal, but they did not mention it. They never mentioned about the height of what? The canal. So this one you're going to look into it when you're answering questions. All right. I think I have mentioned a lot of things that are to be explained whilst you're answering our questions. But anyways, it is good for those who are not on membership, so that at least you can use that information to answer your questions. But for those who are part of membership, we are going to have questions which gives us the difference between the two. So that is it. All right. We are going to look now into the calculations that are to be done. As we said, we are going to need the second area moment to the first. So in order for us to use these formulas for a condition that we are using, for this condition that we are using, where the tank is below the water surface, our r is the distance y. It is the distance y. Always our r is going to be equal to y. If we are using this condition where our tank is below what? Below x-axis. All right. For those who are using their diagrams above the x-axis, you must calculate, you must determine that r. But in our case, our r always, each and every question that you're going to answer, your r is equal to y. Always, guys. I'm not going to repeat this. R is equal to y. So when you say r squared, it's y squared. Each and every question that you're going to answer, as long your tank is below the x-axis. But when it is above, do not say I said always there. For those who are using this one above, you are going to calculate it, of which, guys, I do not want to bring confusion. I explain this tomorrow. I just want to maintain to what I have already explained before. Then our dA is always, again, a fixed thing, as these two areas are identical. The strip is for what? For y. So our dA, it is something that is fixed. Remember we said our dA, two identical portions, it is going to be 2x dy. So this is our dA. Always, always, guys, always you're going to use this. These two, they are not going to change. So just take this part, you know that it does not change. So these are things that you just need to substitute there. R squared, y squared, your dA, 2x. So 2 for what? Two identical portions. X in terms of what? X in terms of y, remember, just like that. So x is the relationship between x and y, x in terms of y. So that is it. So let us just have our steps so that we can easily follow them. But with this information that I just gave you guys, we can even start answering questions. But anyways, let us just write important steps to follow. All right, let's just say steps to follow to apply the formula. Number 1, simply draw a fully labeled cross section of the container holding the water on the system of axis. Like from the information that you're given, just be able to draw a fully labeled A fully labeled cross-section. Cross-section, right, of the container holding the water, which is of the container holding what? Holding the water on the system of axis, meaning to say here, okay, then we have got two things. The x-axis as the water surface, or the x-axis can be the bottom of the container. There are two things. But with this calculation that I'm working with you guys, I'm going to use my x-axis at the water level. So my x-axis, I'm going to take it at the what? At the water level. At the water level, which is our water surface. So thus the tank, or whatever that you're going to have, guys, that is holding the water, the tank is below the x-axis. It is below the x-axis. So in our presentation, this is what you're going to use, guys. There are so many different teachers on YouTube and this and that. You can follow other calculations or other presentations that they do. You might understand that one, but for us, this is what you're going to use since we have already applied this. Yes, for sake of revision, we're going to look into others if we've got time. All right. Sorry, I just mentioned the x here. I need also the y. So the x-axis is going to be our water surface. Then the y-axis is symmetrical, as we saw. It divides our graph into two equal parts. So the y-axis is drawn through the middle of the container. So it is a symmetrical line. It is a symmetrical line. That is, it divides uh, the container into two equal parts. Divides the container into two equal parts. Into two equal parts. Into two equal parts or portions. Okay, so this is the condition of the y-axis. All right, number 3. Always here use the horizontal strip. Always use the horizontal strip. Always use the what? The horizontal strip, which is the strip for y. So that's our strip is for y. Always. So therefore, if we are using this because of our condition that the tank is below, guys, these are the notes for someone who is using the tank. Don't take these notes if you are using your tank above the x-axis, please. If you are using that one, just watch another video. For now, do not take these notes, okay? So therefore, we're going to consider what I explained before. R is equal to y. We're going to just take that one for here. R is equal to y. Okay, then 4. This one is direct. I explained it. Number 4. You must find the relationship between x and y. Find the relationship. Find the relationship between x and y. Between x and what? Between x and y. As we saw that we are dealing with the strip for y, so we must integrate with respect to y. So therefore, x must be written in terms of what? In terms of y. X in terms of y. Okay? From where? Where are we finding this relationship from? we are going to find this relationship from the given. This is what you're going to use. You find the line that represents either side, the sides of the tank, either side, like here, for this one, this side, the equation of this side. If maybe we are given something like a trapezium like this, you can find the equation of the line of this side, either side, this one, or you can find this one. All right. So there are some that just combine them at once. But in our case, we're just going to use one. You find the area of either side, either this one or this one. So it's either this side or this side, the equation. All right. So that one I'm going to explain while you're doing question papers. We shall see it. All right. So this is the equation that I'm talking about, the relationship between x and y, but you must have x in terms of what? X in terms of y. So this relationship, it represents from, or let us just say from, all right, from either side, from either side of the container, not the base, but the sides, the other sides. Like if you're talking about this will be our base of the, so you're talking about this side, either side, all right? We are given a triangle like this, it will be isosceles, so it's either side. Remember the concept. So this is it. We are going to look into that one. All right. Then the distance r is already explained here. Remember, we talked about the distance r is equal to what? R is equal to y. So I'm not going to talk about that distance there because we already have it, unless if you are using that one for those who are using above the x-axis. Then you must find your moments. Find the first and what? And second. Find the first and second moment of what? Moment of area. Which is moments of what? Of area by integration. We know this one is done by what? By integration. We know this one, guys. So you're going to integrate. Then you must find the last thing. From these two, the first and the second moment of area. Remember, those are the ones that we need here. Those are all this. It is for us to have those here. The second and the first. So therefore, you can calculate what? We can calculate the depth of the center of fluid pressure as our last part, all right? So that will be the last thing to do. So we must find the depth of what? Of fluid pressure from the first and second area moments. So that is from the second moment of area over what? The first moment of area, as I mentioned before. Just like that. Just like that. You're done. With our question, with this aspect of answering our question that we are going to use, where our tank is below the x-axis, the first area moment is always, or will be always, a negative. The first area moment will be always a negative. So therefore, the depth that you're going to have is going to be a negative as well. So you must obtain a negative value there from this part that we are using when our tank is below the x-axis. Just like that. You must have a negative value. And also the units, all right? So second moment of area, guys, we talked about these units when you're dealing moment of area. That's units to the power of 4. So these are meters. And the first moment of area, it's units to the exponent of 3. So these are cubic meters if you had given your units in meters. So that is what you're going to use. All right. Is there anything that I can add? All right. I think most additions, we are going to have additions on the other part. Okay, let's just see one or two before I conclude. Also, the shapes. Let me just sketch one or two shapes. For those who are not on membership, they can maybe take advantage of that and use those for revisions to be used later on. So, like I said here, guys, it's just substituting your y in there in place of what r, your dA. So your first area moment is just gonna be direct, just a direct substitution. Direct substitution. All right, let's just consider the possible shapes. Possible shapes. Then we conclude our class. We are going to look into examples. In our next classes, we are going to work with different shapes that are in our syllabus. So we can be given a trapezium. So it's actually a regular trapezium that you'll be given. The reason here it is because of being symmetrical about the y-axis. Remember the y-axis concept. So here I'm just giving a sketch. I'm not saying always it is going to be a condition where it is attached, where it is to the x-axis. Here I'm just giving a basic of the shape. So this is your x-axis, y-axis. All right. So that is what you're gonna have. Our limits from what? From A to what? From A to B. So A and B, so this will be your strip covering the two sections. So these two portions, they're equal. All right, this side and this side are equal. The portions, this portion and this portion, they are actually the same in terms of their area. So this is it. This is our Y. This is the strip, horizontal strip. And so for the equation, you use this point, the points which are on the line, you can use this line or you can use this one. All right. But this is the shape that you're going to use. So these points, they're important. This one and this one, they are very, very important to know. And also the limits. Okay. We are going to talk about that later on. Number two, we can have a rectangle in the form of a rectangle. All right, so in the form of a rectangle, it's just gonna be something, guys, it's just a sketch. I'm not saying it's gonna be direct like that because I'm not considering to say it is 1 meter below, it is 2 meters below. I'm just taking a sketch. So the y-axis is symmetrical, so you're gonna have same distance. All right, this will be your strip, horizontal strip below the x-axis, and this is our y. Just like that. So this will be our limits from A to what? From A to B. Okay, what else? So the equation will be this. You can use this line or use this line. Since it is a vertical line, the equation, it will be x is equal to A, the value of A, which is at this point. That's the equation that you use. That's your relationship. A horizontal line, I mean, a vertical line, it cannot be written in x in terms of y, guys. It's impossible. It is x is equal to the value where it is passing that vertical line. So that will be your equation. But here you must calculate, use the 2 points, this point and this point. Y is equal to mx plus c. As you can see, it's a slanted line. Then we can make x the subject from there. All right. They can give us a rectangle. It can be a square. Just one and the same thing. All right. It can be a triangular, which is from a triangle. So the triangle, just a sketch. It must be an isosceles triangle. Why? Because the y-axis is the line of symmetry. So it divides our triangle into two equal parts. All right. Always your horizontal strip, always. This is the distance of y that you're going to have from A to what? From A to B. This is just a sketch, guys. All right. So as we can see, this is what you're going to have. So the relationship between x and y is to be found from, we can use this line, all right? So you can use this line. So it's a straight line. We can use the points. So use the point. There's a point here. There's a point. Y is equal to what? Mx plus c. You find your relationship. Then you make x the subject of the formula. All right. It can be a parabola. All right. It can be a parabola. It can be a parabola. For a parabola, using the concept that it is symmetrical about the y-axis, it turns that the y-intercept will be our turning point, like this. The y-intercept here, it will be our turning point. So our y-intercept, it's our turning point. So from A to B, the strip, always horizontal strip is used, and this will be your y. So you are going to find the equation, of which the equation of a parabola, its y is equal to, for the one that is in this case symmetrical about the y-axis from your grade 10 mathematics. It is y is equal to ax squared plus what? Plus b or plus c, where c is our turning point, or the y-intercept. Y-intercept, or our turning point. So you must calculate the value of a, then you make x the subject of the formula, as our relationship is always x in terms of y. So you're going to make x the subject. All right. It can be a semicircle. Last one, just gonna be a semicircle. Remember below the below the x-axis, so you cannot have as a complete circle like this. We just need something below the x-axis, so that's why at the end it will turn, it is going to be a semicircle. So a semicircle, same units. This is radius, so this is radius, this is our radius. So that is the condition. Our horizontally strip always the distance of our y, like that. Okay, so this is what you're gonna have. So remember, it is a semicircle, so below the x-axis is the one that you're considering. So you take it from the equation of a circle. X squared plus y squared is equal to r squared. But our relationship, x in terms of what? In terms of y. So you just make x the subject, which is going to be square root of, if we make x the subject, it's going to be r squared minus y squared. So this is your relationship that you're going to use. So guys, that's a semicircle. Yeah, everything is there, the limits and this and that. So pay attention to the question. These are just sketches. I'm not into the question, because the question, they can tell us it's 1 meter below, it is 2 meters. I'm not considering that. I'm just giving you a basic view of how you must look into these questions when answering, when the tank is below what? Is below the x-axis. So in our next class, it shall be revision of each. So we shall start, I don't know with which one, but we shall cover these on separate classes, each on its own, each on its own. So make sure that you join the membership so that you do not miss any of the classes that you're going to have on these explanations. And each and every class that you're going to have will be backed up with question papers. We are going to have a few examples, then more question papers, or just question papers to balance how questions are given. So that is it, guys. The depth of the center of fluid pressure. So let us meet in the next class.